This is question 6 from the 2023 AP exam, and it's a little bit of a combination of atomic structure as well as thermochemistry, thermodynamics as well. So let's take a look at this first question where we're comparing these compounds HBr and HF, and we want to list the intermolecular forces present in these compounds. So by the way, intermolecular forces. So I know that the answer will be more than one, and I like to actually just maybe sketch out the Lewis dot diagram to visualize what they look like. They're very similar. So HF is asymmetrical, and it's polar. And when it's looking at the polarity, what I actually know is that the fluorine is the negative dipole. It's more electronegative. And the hydrogen is the positive dipole, which I use this little delta positive to show. So knowing that it's polar is going to help me determine this. And HBr, very similar, with bromine being the negative dipole and hydrogen being the positive dipole. So you guys may remember from class that, or just from your class, your school, that all molecular compounds showcase London dispersion forces. I'm just going to abbreviate it LDF. So no matter if you're polar or nonpolar, everything showcases London dispersion forces or van der Waals forces. And by the way, those are the only forces between nonpolar molecules. So everything will showcase that. Now, because these are both polar asymmetrical molecules, both of these will also showcase dipole-dipole interactions. And that's because each of them has a dipole, right? Each of them is a positive and negative dipole. So they will have, if, for example, if I have another HF molecule beside my original one, the delta positive of the hydrogen will have an attraction to the delta negative of the fluorine. Now, the difference with the HF versus the HBr is that the HF will also show hydrogen bonding. So hydrogen bonding, look at your notes. It is the bonding between the positive hydrogen with Thon. So either fluorine, oxygen, or nitrogen. For example, we see hydrogen bonding in water, and we will also see hydrogen bonding in HF. These are the most electronegative elements. So they have this is actually a stronger IMF, intermolecular force, even stronger than dipole-dipole. Okay, so very similar compounds, the difference being that this one's more electronegative, so it'll show hydrogen bonding. So in the next question, actually this is similar to what I just said. So it says here, based on the relative strengths of intermolecular forces, explain why this delta H of vaporization, which means the enthalpy it takes to vaporize, to turn the liquid into a gas, what you see is that the HF has a higher enthalpy of vaporization than the HBr. Well, again, if we go back to our chart, we can hopefully answer this. It's because we have stronger intermolecular forces in hydrogen in HF, so which is, by the way, it's the hydrogen bonds. Okay, so that's the stronger intermolecular force. So this stronger intermolecular force is going to result in more energy for you to separate these HF molecules away from each other. So these guys. So to change this into a gas, we need to sever this hydrogen bond. We need to separate those molecules out so that they become really far apart from each other and turn into the gaseous phase. Okay, so what did I write here in my answer? Stronger intermolecular forces in the HF due to an H bond requires more energy to separate the H bonds to turn it into a vapor. You can look at the AP answer key to word this a little nicer than what I'm wording it, but hopefully you get the idea as I'm talking you through my thought process, okay? And then in the next part here, it says calculate the thermal energy in kilojoules required to vaporize 6.85 grams of HF. So if you guys look at the data table up here above, this is the amount of energy or enthalpy I need to vaporize 1 mole of HF. So I don't have 1 mole of HF here. I only have 6.85 grams. So let's first figure out this 6.85 grams. How many moles is this? Okay, I like to use the mole formula, which is N equals M over M. So I'm going to convert the grams of HF, 6.85 grams, into moles of HF. Now I'm going to use my data table. Molar mass for HF is 20.01 grams per mole. Grams cancels out. So I have a mole value here, 0.3423. Okay, now, so this is moles of HF. Okay, now that I know this, I want to calculate the new delta H. So this is what you do. It's a unit cancellation. I'm going to take the value I just calculated. So I have 0.3423 moles of HF. I'm going to multiply this by a ratio. This is how I like to do these questions. And in my ratio, I want to cancel out the unit I don't want. I don't want moles of HF, so that's going to go on the denominator of my ratio, so that moles of HF will cancel out with moles of HF. I do want the kilojoules. And so what do I fill in my ratio? We need to go back up here. I know that for every 1 mole of HF, it takes 25.2 kilojoules of energy. Okay, so when I multiply this out, again, the moles will cancel out. I will get a delta H of 8.63 kilojoules positive. So that makes sense. It's proportional. The enthalpy is proportional to the amount I have. So if I have less HF, it makes sense that it takes less energy, only 8.63 kilojoules to vaporize it, to turn it into a vapor. Okay, and that's how we do a problem like that for unit cancellation. And also a note that my final answer is to 3 significant digits because I'm given 3 significant digits here in the question. So that should match as well. And finally, in number 6, based on the arrangement of electrons in bromine and fluorine atoms, explain why the bond length in HBr in the molecule is greater than the HF molecule. So if you have your periodic table near you, that'll actually help you answer the question. But if you actually look at your periodic table, bromine is way further down than fluorine on your periodic table. So bromine, actually, the further down it is, it has more energy levels, right? So what I actually know is that bromine has a greater atomic radius than fluorine. So when bromine is bonded to hydrogen, because this radius is so big, that means the bond length is going to be longer in HBr. So bromine has a greater radius than HF. That's why, therefore, the bond length in HBr is greater than HF. Now, if you want to get into more detail to support your answer, you can explain why bromine has a greater radius. It has a greater radius because we have more electron orbitals in bromine. If you do your quantum electron configuration, you can see that bromine goes up to 4, like n equals 4, in terms of like 4 principal energy levels away from the nucleus, whereas fluorine, this radius, there's only 2 energy levels. It's n equals 2. So you can include that in your answer as well for that additional detail. All right, hopefully that helps you answer question 6, and you can check out the other videos if you need help with solving other questions from the 2023 exam.